right, Lewis structures, double bonds. So all these will meet that criteria. You're going to not have enough electrons when you finish drawing your basic Lewis structure using the steps, which means you need to double or triple bond. So let's get started with this. So CO2, you have 4, group 4, right? Oxygen, group 6. 6 times 2 gives you 12. So 16 valence electrons. Carbon's in the middle. Why? Because you have less of it. Technically, it's whatever is most electronegative, but, you know, shortcut works too. Carbon's always the middle. O, by the way, is a little more electronegative, so technically that rule doesn't apply all the time either. But anytime carbon's involved, stick it in the middle. That's the simplest thing to do. Whatever you have less of, stick in the middle. You'll be right majority of the time, if not all the time. All right, so 16 electrons. First thing are connections. We use a total of 2, 4 to make the connection, so that means you have 12 left. So 2, 4, 6, 8, 10, 12. So there's all your electrons. Now what do? Well, if you look at it, you realize that the middle only has 4 electrons. The outsides are good, but the middle is not good. So what do? We do our fancy erase and move technique. So we're going to erase from whatever one has more electrons. So in this case, one of the O's. Doesn't matter which O you start with. No, it makes no difference. But typically, it's whatever one has the most. They both have equal amounts, both O's. That's why we can get away with it. Because you just erased and moved, this O is still happy. It has 8 valence electrons. You need to go back and fix it, right? Now, look at the middle. 4, 6 electrons. Still short, so we erase and move. So what do we erase and move from? Not from this one, because this one doesn't have more electrons anymore. This one does, so we move from there. So erase and move, and there you go. 2 double bonds. That's the correct Lewis structure. Everything has 8. Everything's happy. And you can see the reason for this because you had a shortage of electrons. So determine the shape. You have 1, 2 bonded domains. That's going to make it linear, like a line. Kind of looks like a line already. Polarity. Well, dipoles cancel out. So that means this is going to be non-polar because the dipoles cancel out. There's symmetry there. And as far as your IMFs, just LDF. Nothing else because it's non-polar. LDF is the only thing you can write. Next, HCN. Same thing. 1 plus 4 plus 5 gives us 10 electrons. All right, so C in the middle, N on one side. Now, what do you do with the H? So what you usually want to do is try to put it off the middle. There are exceptions, but for the most part, you try to go off the middle before you start putting it off the outside atoms. This is a little quirk. So when you're drawing the Lewis structure, you use a total of 4. That means you have a total of 6 left. So 2, 4, 6. There's all your electrons. Hydrogen's already done, right? Once you connect hydrogen, you don't need to do anything else with it. So I'm not even worried about H as my outside element. It has a complete, not an octet, it has a duet. It has 2 electrons, which is all you really need for this. So then what you need to do is sit there and look at the middle and see that it has shortage of electrons. And in this case, it wants to have 8, but it only has 4, 2, 4. So what do? Erase and move. Erase, move. Now does it have 8? Well, 4, 6. No, still has shortage. You take it for whatever has more electrons, right? Remember we just said that a minute ago. So we're going to erase and move. Does it matter if I move this one or something? Absolutely not. Has no difference. As long as you have a lone pair at the end of this whole process, you're fine. There you go. Triple bond. This one has 8, 6 plus 2. This one has 8, 6 plus 2. You're done. All right, structure. 2 bonded domains, linear. Polarity. What do we do with the polarity? Well, if you take a look at this, you have a linear structure, so you would think it's symmetrical, so that means it's non-polar. No. H and N cannot cancel each other out. They're not the same element. The only time you have symmetry that can cancel out is if the same element is on opposite sides. That's the only way they could fight each other off and bounce each other out, right? So this does not. So this is actually polar, surprisingly enough. LDF guaranteed, because everything has LDF. And because it's polar, dipole, dipole. And that's it. There's no H bond because even though there is an H, it is not attached to the N. Remember, it has to be one of the fun molecules. If it's not attached, if H is not attached to one of these 3, there is no H bond. SO2, 6 plus 12, 18. So we're going to go through our steps. Do not skip steps. Some of you guys are probably going to start trying to skip steps in order to anticipate when you do it. Don't do that. Put all your electrons down using an eraser. Trust me, it'll save you a lot of headache. So 4 electrons, 6, 8, 10, 12, 14, 16. Now, the most common brain fart in this, I'm going to put a lone pair off of one of these, between one of these S and O's and say, oh, that's what has to go. No. You only put a double and triple bonds when you're short. You don't know if you're short yet. You haven't put all your electrons. You have to put all your electrons on before you know there's a shortage. So I'm going to put it there. And I know you're saying, well, I know there's going to be 6 here, so that's going to be short. Doesn't matter. Don't skip steps. That's the recipe for disaster every single time. And we don't want disasters. So now comes the next part. S doesn't have an octet. It only has 6. O's are happy. So I'm going to do erase and move. Erase and move. Now, when I erase and move, this has 8. This has 8. Everything has 8. You're done. Now, notice I could have done the double bond here or here. Both of these are valid. So guess what? It's a resonance structure. And as is typical resonance structures, you need to draw all variations of it. Now what you do, draw these little 2 cute arrows pointing toward each other to indicate that, and you're done. What happens if you forget this? You are wrong. Are you going to be told there is a resonance structure you need to draw over? No. You need to realize there's a resonance structure because you had a choice where the double bond goes, and then draw all the variations you can. So be aware of that. All right, so as far as the shape, you have 2 bonded domains, right? 1, 2. Double bond counts as 1 domain, in case I didn't mention that earlier. You don't count the number of electrons here, you just count it as a region of electrons. So 1, 2 bonded domains, 1 lone pair. So 2 plus 1, basically, right? That's a bent structure. And bents are always polar, but even if you didn't know that, look at the lone pair off the middle. That is polar. Now, some of you guys are looking and say, well, it's a resonance structure. Doesn't that mean it's non-polar? Lone pairs trumps everything. There's a lone pair in the middle. It is automatically polar. End of story. So LDF, guaranteed, right? Then dipole, because you said it was polar. Sorry, my writing's very ugly. All right, so then you're done. There's no H bond because there's no H's. All right, SO3, you have 6 plus 18. 6 times 3 gives you 24. S in the middle. 1, 2, 3. All right, now what do? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. There's all your electrons. Then you look at the middle. Does the middle have 8? No, it doesn't. The most common thing I see with these kind of questions, students forget to look at the middle. Never forget to look at the middle. Middle is very important. And that's what you want to do last, always. Look at the middle. So I'm going to erase the O with it. Not what I was shooting for, but I'll just put it back. All right, so I erased the electron here, and I put it here. What's a common brain fart I see with this kind of stuff? Someone will take an electron from here and stick it over here. Why? Why would you do that? Now you gave this O 10 electrons. What are you trying to accomplish? Follow the steps. Wherever you erase from, it has to be shared with that element. You can't just give it to another element and say, here, have a nice day. Does not work. Now, you could see there's a resonance structure because you could end up bond here, here, or here. So what does that mean? You need to draw 3 variations. I'm not going to draw it for you. You can figure it out yourself, but be aware if you didn't, you would get dinged. All right, structure, 1, 2, 3 domains, trigonal planar. All right, polarity. Well, we know that trigonal planars are typically nonpolar, but we also know resonance structures without a lone pair are also nonpolar. So we have 2 different reasons to call this nonpolar. What's your IMF, LDF, and you're done. Why? No dipole, because you didn't put polar here. If you don't put polar here, I better not see dipole here. All right, SCN. S6 plus 4 plus 5. That's a total of 10, 15. And then the negative charge gives you 1 more. So 16 total electrons. Remember, you add when it's negative, you subtract when it's positive. Whatever the negative number is. This is a 1, so that's why I added 1. This was negative 2, I would add 2. All right, so what's my middle? C, because it's there. N, and then S. So that's 4 electrons. 6, 8, 10, 12, 14, 16. Look at the middle. Doesn't have 8. Very unhappy. So what do? You erase and move. Which one do you erase and move from? Here, it doesn't really matter. I'm going to move from this one. You could have done either one and you've been fine. All right, this still has 8. 6. That's not what I'm looking for. So erase and move again. Do I move from the N? No, because that's not the one that has the most electrons. This one does. You always take from whatever has more. There's your double bond. Now, some of you guys were like, why can't you do a triple bond? There's a whole explanation involving formal charge that can explain this, but we're not going to do that. Just don't do this like that. That's also what I'm going to say. When you get to more advanced chemistry, then maybe you have to do formal charge and figure that out, which isn't really hard, but it's outside the scope of what we're trying to do here. The last thing you need to do, the brackets and charge, because you have to tell the person, hey, this is a polyatomic ion. That's why I have 16 electrons instead of the 15 you would anticipate if I didn't put these brackets and charge in it. All right, shape, 2 domains, linear. Remember, the shape is always based off the middle. All right, polarity, well, there's no lone pairs off the middle, but you have N versus S. Are they the same element? No, they are not. That's polar. They can't cancel each other out. So LDF automatically, and then you have dipole. I'm going to just put DD here because I'm tired of writing the whole word. Plus my writing's really bad. All right, last one. You have C2H4. That's 2 times 4, 8, plus another 4 gives you 12. All right, so what do? 2 carbons. If there's multiple carbons connecting to each other first, that's your secret for this. If there's 3 carbons, you would connect those 3 carbons first. If there's 4, you would connect them first. That's the secret for handling multiple carbons. Connect them before you do anything else. And typically what happens, they're going to be mirror images of each other. It means that the left and right side should look the same. So if you have 4 hydrogens, don't give 3 to one and 1 to the other. Share them equally. So 2 to this and 2 to this. All right, so we had a total of 12, 2, 4, 6, 8, 10. You have 2 more. Stick it off the carbon. Doesn't matter which one. No, it doesn't. But I'm sure you noticed this carbon only has 6. That's not a good thing. What do we do? Erase and move. So what do we erase and move from? Can't do it from the H's because there's no lone pairs off of them. You have to erase that lone pair just put there and then stick it between them, and then you have the proper structure. So there's a double bond between the carbons. So remember, if you have multiple carbons, connect them, make them look like each other. See how the left side and the right side look identical? That's what you're shooting for every time. All right, shape, 1, 2, 3 domains. So I know what you're looking like. Wait, 1, 2, 3, 4, 5. No. Look at 1 carbon only. If you have multiple metals, look at 1 at a time. Now, in more advanced situations, they would ask you for what is the shape of this one? What's the shape of this one? For our purposes, for the most part, they're going to look identical shape-wise. You just have to name one of them and you're good to go. So I'm going to look at one of my metals. These are 2 metals here. I'm going to look at 1 carbon and say, okay, well, this carbon has 1, 2, 3 domains. That's trigonal planar, right? That's all you got to do. And I know what you're saying. What if you looked at the right one instead? Well, look at the right one. 1, 2, 3 domains. Still trigonal planar. That's not a coincidence. So that's how you handle those. Shape is going to be trigonal planar. Sorry, polarity is going to be non-polar. Now, why? Trigonal planar is usually a non-polar, but also CNH only. What is that always going to be? Non-polar. If CNH is the only element involved, it is always non-polar. You add any other element, O and F, doesn't matter, becomes polar. It's simple as that. All right, so LDF, as always. And then your second structure, you have dipole-dipole. I'm going to spell it out this time. So there you go. And there's your 2 Lewis structures. Or excuse me, there's your Lewis structure and your 2 IMFs. And that's how you do it. That's how you do it when you have double and triple bonds, which means you have a shortage of electrons.